I've got a problem up on the board for you to try. For this problem, we are approaching the origin. I promise we are going to do a number of examples where we're approaching a different point. It's going to be a little while before we get there. There's a specific reason I wanted to be approaching the origin in this case. And then in the next video, I'm going to show you a technique that only works if we're approaching the origin. And then we'll get back to some examples where we might approach some other points. Okay, so I want you folks to try this one on your own. I'm just going to caution you to be very, very careful about using very accurate notation as you make your substitution. So pause the video, give this one a shot, and then tune back in and we'll keep going. Welcome back. Okay, I can see that I can't plug in the origin because of course the bottom would go to 0, the top is approaching tangent of 0, which is 0, so we have this indeterminate form. And it is very convenient that I've got this same expression, x squared plus y squared, that's causing trouble on the top and the bottom. So I can do a substitution. I'm going to let u equal x squared plus y squared, and I'm going to just rewrite this in terms of u. So I can say this is the limit. So I'm actually saying this is equal to the limit as u approaches 0 from the right. We are getting a one-sided limit here, okay? That's because if I take a look at u, this expression can never be negative because it's a sum of two squares, okay? So don't just assume that you're always going to get a two-sided limit when you make a substitution like this. Sometimes you do. In the last example we did, in this example though, this expression can never be negative. So this is a one-sided limit. And it turns out that's actually quite important. There will be plenty of examples where if you just took the two-sided limit, you'd get the same thing as the one-sided limit, but it's only correct to say that this is equal to this one-sided limit. It is important to acknowledge that, and it is going to make a difference in this case. This becomes tangent of u over u squared. Now, of course, the substitution can't change the fact that we've got an indeterminate form, so I do still have top and bottom going to 0, but now I can L'Hopital it. So I can say this is the limit as u goes to 0 from the positive side of secant squared u over 2u. Okay. Well, now I still can't plug in 0 because the bottom is still going to 0. But I can't use L'Hopital's rule again because I no longer have an indeterminate form, because the top is going to secant squared of 0. Secant is the reciprocal cosine. Cosine of 0 is 1. So secant of 0 is 1, and 1 squared is 1. So the top is going to 1. That's not an indeterminate form. I cannot use L'Hopital's rule a second time. Now, I've got 0 in the denominator, but not in the numerator. Okay. When that's the case, there are 3 possibilities that I can have. Let me just write that out over here. Okay. If the bottom goes to 0 and the top does not, doesn't go to 0. Okay, there are 3 possibilities for what the limit could be. Could be positive infinity, could be negative infinity, or it could be DNE for does not exist. Okay. This function, if looking at this as a function of u, if I were to graph this, there would be a vertical asymptote when u was equal to 0. Okay. I know that with a vertical asymptote, sometimes I get a picture that looks like this. That would be the limit going to infinity. Now that's this function here of one variable. Okay, I'm not graphing the function of more than one variable, although it's having the same behavior. So if it's going off to infinity, there would be a vertical asymptote. It just wouldn't be a two-dimensional graph like this. I could have that we go to negative infinity on both sides. I could have, when I have a vertical asymptote, that we go up on one side and down on the other. In a situation like this, the two-sided limit would not exist. But this is not a two-sided limit. This is a one-sided limit. We're approaching 0 from the positive side. Okay. So to determine which of these it is, I need to just do a sign check. This is sort of some informal work that I just do off to the side here. I say if the top is approaching 1, the top is going to be positive. The bottom is 2u, but u is approaching 0 from the positive side, so u is a positive number. So the denominator is also positive. A positive divided by a positive is positive. So this one-sided limit would be infinity. Okay. Now, there aren't any examples in the book where you get infinite limits, but you still can. Anytime you have a situation where the bottom goes to 0 and the top doesn't, your function is blowing up. It's getting big, and it could get big in positive or it could get big in negative. If it gets big in both directions, then we would say the limit doesn't exist. So we have these same 3 possibilities for things, and you do just need to do a sign check. Okay. So in this section, there's some additional homework not from your book that I've written, and that's basically because the book doesn't actually give you any examples with infinite limits. And the book also doesn't really talk about this idea of substitution, which I think is a really incredibly valuable tool for evaluating limits. So make sure that as you're doing the homework, you're doing the problems that are assigned out of the textbook, but that you also do the additional problems that I've written. Okay.